Back level 2 physicists to continuing on with the electrical systems external. Today looking at measuring circuits and resistivity. So in order to understand how the effect of measuring a circuit actually affects the results, consider the observer effect. Okay, so when taking a scientific measurement, basically the act of taking the measurement affects the result you get. So in the example here we see the very act of taking your blood pressure increases your blood pressure, you become a bit nervous, which heightens the reading you actually get. That's known as the observer effect. So the observer effect can also be seen in circuitry because we have to measure the voltage and current with a particular component. So a voltmeter for measuring the voltage and an ammeter for measuring the current. Okay, and the actual introduction of those measuring devices actually affects the values that they record. So what does that mean? Well, looking at the ammeter, it's hooked up in series with the component being measured, and the ideal ammeter will have a resistance of 0 because we don't want it to actually impact on the measuring of the current in that circuit. Okay, but what happens if it does actually have a resistance? Well, for the example here, the ammeter has an internal resistance of 1 ohm. So therefore, the total resistance in the circuit will now be 5 plus 5 plus 1, which is 11 ohms. Therefore, if we use Ohm's law, rearrange it, the current will be total voltage over resistance, or 10 divided by 11, or 0.9 amps. We're actually reading a lower value for the current than there actually would be if we actually hadn't measured it because of the internal resistance in the ammeter. The same is for the voltmeter. So a voltmeter is hooked up in parallel with the component being measured, and we want a resistance basically which is infinite. The reason why is we want to measure the potential difference in the component, not the potential difference involving the voltmeter. So we want the current to go essentially all through the component, not the voltmeter. And how does this affect things? Well, in this example here, when we have a voltmeter with a resistance of 20 ohms, well, you'll see that now the resistance of the system changes, okay, because you've got that voltage voltmeter in parallel with R1. So it means that the resistance there is now 1 over 20 plus 1 over 5. The inverse of that, or 4 ohms, because it's in parallel. And then we have the 5 ohms in series, so 5 plus 4 is a total resistance of 9 ohms. Therefore, using Ohm's law, the current going through R2 will be 10 divided by 9, or 1.1 amps. That is, of course, shared in the parallel circuit between the voltmeter and R1. So therefore, that the voltage is going to be 4.5 volts now for the voltmeter and 4.5 volts for R1. Okay, so it's going to actually not measure predict the voltage of R2, because 5 ohms plus 1.1 amps will give 5.5 volts, and it'll be under predicting or under measuring R1, which will be 4.5 volts. Okay, so another concept you have to know in electronics is the idea of power. Okay, so remember from last year that power, the symbol is capital P and the units are watts, capital W. And the new equations are P equals VI. Okay, you can then substitute Ohm's law, V equals IR, into the equation, which will then give power equals I squared times R. Okay, and also power equals V squared divided by R, because all you're doing there is substituting the current as being V over R. And different devices have different powers. Okay, so here's a number of devices used in the home. And you'll actually see those that require heating of air and water require the most energy transfer. So, for example, a hairdryer up at 2,000 watts, toaster about 1,500 watts. So that's where most of the energy is in a home, heating of water and air, whereas something like your game devices or DVD players are only about 15 watts. So if you want to save electricity, then turn off your heating. And finally, looking at resistance, what affects the resistance of a wire? Well, that will be the area, the cross-sectional area, the length of the wire, and the material. and that's related to a concept called resistivity. Okay, so the way I think about it is about sucking milkshake out of a milkshake container with a straw. The longer the straw, the harder it is, so resistance is proportional to the length. And if you increase the width of your straw, then it'll be easier to again suck that milkshake up, so resistance will be proportional to 1 over the area. Okay, so then we get the idea of resistance being equal to the length over the area times the resistivity. So the resistivity essentially is based on what the material is. Okay, so in terms of resistivity, resistivity changes depending on the material used. So for example, nichrome is got quite a high resistivity, so the high resistance for electricity passing through. That's why nichrome is used in heating mantles, because it heats up the nichrome. Electricity passes through, heats up the wire, therefore it's being transferred into heat energy, whereas copper and silver are very good for wires because there's less loss to heat because they have lower resistivity. And that's pretty much all there is for today.